Welcome to this lecture on proving identities. And the entire chapter is pretty much about using identities and formulas to manipulate them and perhaps get an identity into or a trigonometric expression into a simpler form. Before we get started here, there have to be certain basic trig identities that you need to memorize, such as the ratio and reciprocal identities, with which we're quite familiar by now, so tangent and the cotangent, and then the secant and the cosecant. The Pythagorean identities, we should definitely have the first one memorized. Sine squared plus cosine squared equals 1, and then the other ones, they help also it helps also to have them memorized. Tangent squared plus 1 equals secant squared, and the other one respectively. Make sure that you know where to find them in the book. Guidelines for proving identities. The current textbook that I'm using at the time of recording lists 5 guidelines. Notice that I added a 6th. So here they are, as we're proving identities. Work on the more complicated side first. Substitute basic trig identities to simplify the expression. Look for algebraic operations that simplify the expression. For example, adding fractions, distributive properties, factoring, specifically the difference of squares. As we're going to go through examples and problems, we'll encounter all of these guidelines. So look out for them. If you cannot think of anything else, change everything to sines and cosines and continue. That's because the basic trig functions are the sine and cosine. Always keep an eye on the side you're not working with to make sure that you're working toward it. Spelling error, not spelling error, still working toward it. As an alternative, and this is what I added, cross multiply between sides and or manipulate the other side as well, and you will see that. So let's get started with some examples. I'll be referring to all of these, but of course I'm not going to mention them by number 1, number 2, or something like that. Okay, prove the following. Sine times cotangent equals cosine. I'm just going to retype this here by copying and pasting it. And of course, that little gray bar that you see here is all these symbols here for the equation editor. So here on my second line, this is all going to be algebra. So I'm just going to rewrite the previous line and then manipulate it. Sine and cosine can't do anything about it. I'm supposed to work on the more complicated side first, though, and the one that I may want to focus on is the cotangent. Cotangent theta is the same as cosine over sine theta. So that's what I'm going to do. So cotangent is the same as cosine over sine. And at that point, I'm actually kind of done. I'll be rewriting it here one more time. But we can see that the sine is canceling. That sine is canceling off this sine here. And what survives is the cosine. And we're done. Okay, at this point, I would actually like to have large letters here. Done. Let me just do this here relatively quickly, just a household issue of doing this and making everything blue in my lecture. Okay, that hopefully will work a little bit better for me. Okay, one more thing. I also like to have this in bold. There we go. And none of it actually in. Okay, I like to have everything in bold. I'll be with you in just a moment here. I know I should have done this before. the lecture, but I didn't notice it. Okay, I think I got it now, hopefully. Okay, at this point we're done, and here I may want to point out, of course, I used a ratio identity. I think I just tried ratio here. Okay, prove the next one. Tangent plus cosine equals sine times secant plus cotangent. Looks like the expression on the right is a little bit more complicated. The one on the left is actually not that easy either. What we may want to, what we may not want to encounter is a single trig function plus another single trig function. So maybe if there was a square in there on somewhere, it might help, but it's not the case. These are actually a little bit tougher, but let's see what happens on the right-hand side. Okay. What I'm going to do on the right-hand side is I multiply the sign inside. So I'm going to look at the ratio identities here. The secant x, of course, is the same as 1 over cosine x. So I'm going to do that, 1 over cosine x. And the cotangent, of course, is the same as cosine over sine x. Cosine x over sine x. So what I did now was I used the ratio identities. And now I multiply the sine to the inside. There it is. And here it is. And then I don't need the parentheses anymore. There we go. So what did I just do? I distributed it. Maybe I want to plug in the ratio over here. Ratio identity. Distribute that. And maybe the done at the bottom here. And here cancel. Cancel sine theta. There we go. So distribute here, and then of course on the next line I can see what's going to happen. Here of course the sine x is canceling, and what we have is cosine x. And what we have here is the ratio identity tangent x. And as we can see, we're done. And I may want to write down what I just used as a ratio identity. And canceled sine theta. Okay, prove the next one. Let's see what's going to happen here. Oh, which side looks more complicated? I would say they both look relatively complicated. Definitely the left-hand side even more so. Let's see if we can do something on the right or on the left here. The left-hand side kind of looks to me like a Pythagorean identity with the 1 minus tangent squared, but then I'm checking the Pythagorean identities, and that's not what it says. 1 plus tangent squared, it says. So I might want to be careful and actually not use that one. I could substitute something for the tangent squared, but you know, anything I substitute just might make it more complicated. What do? what I do recognize is that on the left-hand side, I'll not show that on the left-hand side, this here is actually what is called a difference of squares. It doesn't say squares. It says quadruples. But quadruples and sextuples and octuples, or whatever they're called, all the same, I can still take them apart and I can write here, so listen carefully, cosine to the fourth minus sine to the fourth is the same as cosine squared minus sine squared times cosine squared plus sine squared. And you should be familiar with that difference of squares. So that's exactly what I'm going to do. This one is going to be cosine squared minus sine squared. And we put parentheses around here. Times, again parentheses, and where did it end up to? Oh, off the screen. Even for me, off the screen. There we go. There it is. Plus. Okay. And for some reason, it keeps pushing it off the screen here. So what I just used here is difference of squares. How did I know that? Well, that comes with experience, and the more exercises you do, the more familiar you become with them, and you just have to keep in mind all these algebraic, in fact, not trigonometric expressions and manipulations, but actually algebraic expressions. So from previous classes that you should be quite familiar with. So here, difference of squares. Let's see if that works. Well, what I'm going to do here is, on the first one here, I could, for example, divide by cosine squared, but I also could divide on the second one by cosine squared. I can only do one of them. I can't do both. Notice there's a times in between. There's not a plus or a minus. There's a times, so I can only do one of them. But even before I do that, I may want to recognize that the second expression, not the second expression, but the second parentheses, this one right here, what is that? It's a Pythagorean theorem. That is exactly 1. I may want to write that down. There we go. So Pythagorean right there. And now I may want to look on the left-hand side and say, on the parentheses on the left, what can I do there? Well, I can divide this by cosine squared and this by cosine squared. So that's exactly what I'm going to do. In the meantime, of course, I don't need the 1 anymore. I may want to split it up into two fractions and then put a minus in between. The first fraction is going to have cosine squared divided by cosine squared, and the second one is going to be sine squared divided by cosine squared. So here, what did I just do? Divided by the denominator cosine squared. Let's see if what do we have here? Cosine squared x t, cosine squared t. There we go. And at this point, I may want to recognize, well, first term is 1. Second term, which is a ratio identity, is tangent squared t, actually negative tangent squared t, and therefore we're done. Maybe I underline these dones here for later. Okay, prove the next one. What am I going to do here? Left-hand side, I'm sorry, right-hand side looks more complicated. Left-hand side is just a simple 1 plus cosine. What can I do? Here's something that I recognize right away. I have a nice expression of 1 plus cosine on the left and another nice expression, 1 minus cosine on the right-hand side. And here's what I recognize. When I multiply them, I come up with a nice difference of squares. And that's exactly what I'm going to do. So times, actually close the parentheses, times parentheses plus 1, parentheses, and then on the right-hand side. We have this one. So basically what I did here is I cross-multiplied because of, well, I don't even need to use the word alleged, but I do it because of alleged difference of squares. Maybe there's a better word for that. Maybe this one, because I spotted a difference of squares. So now I'm going to manipulate that difference of squares. So you have difference of squares, which is going to come out to 1 minus cosine squared. The parentheses, 1 minus cosine squared. It's a FOIL. The difference of squares, and of course, in the difference of squares, the two middle terms cancel out. And now I'm actually done. I don't need to show anymore because I recognize that this is a Pythagorean theorem. Pythagorean identity recognized as Pythagorean. And therefore, we're done. Okay, let's see what happens next. Prove tangent t plus cotangent t equals secant times cosecant. Okay. Basically on this one, I don't have much of a good idea what to start out with. So on the right-hand side, I'm just going to rewrite them. This one here, of course, is 1 over cosine t. So, oops. 1 over cosine t. And this one here is 1 over sine t. One over sine t. That didn't get me very far yet, as you may notice. At this point, I may want to consider looking at the left-hand side as well and simplifying everything to sines. So what I'm going to do here is I use the ratio identities and simplify everything to sine and cosine. Okay, so I'm going to go in here and tangent, of course, it's going to be sine over cosine. And this one is going to be cosine over sine. Doesn't give me much of a clue yet what's going to happen. In the next step, I may want to pay attention to, on the left-hand side, let's see, on the left-hand side, I have an addition of two fractions. On the right-hand side, I have a multiplication. that really doesn't fit. So what I may want to do is on the left-hand side just get one fraction out of it. So I add two fractions, which means I'm going to look for a least common denominator. The least common denominator is going to be cosine times sine. So as I get rid of this plus here and combine the two fractions, I will come up with a least common denominator of cosine times sine. And here I would have to build up. So on the first one, as I multiply the denominator with sine, of course the numerator needs to be multiplied by sine. So I come up with sine squared. Then I have that plus that used to be in between the fractions. And on the second fraction, as I multiply the denominator with cosine, the numerator also needs to be multiplied with cosine. So I'm going to come up with cosine squared. Cosine squared. So what I did here is added the fractions on the left with the LCD, least common denominator of sine t times cosine t. Okay. What's going to happen next? Well, at this point, I'm actually done. Because notice on the left-hand side, Pythagorean in the numerator on the left. So that numerator equals 1. And therefore, the left-hand side looks identical to the right-hand side, and we're done. Okay, a couple more exercises. And I believe at this point here I will actually stop myself and do a second lecture. I think I've already been here in this lecture here for quite a while. So see you in a moment. Okay, here are the last two examples from the section on proving identities. And I made a faux pas because I had already recorded this continuation and then noticed that I forgot to turn the microphone on. So I'm going to do it again, but because I had already typed, had already done the algebra, I'm not going to reproduce everything. Your benefit might be that it is shorter. The disadvantage is you don't see me developing it right away here. So the first one, let's get started here. The first one is prove this here sine over 1 plus cosine and so on equals 2 cosecant. On this one here, I actually don't really have a good idea on where to start. So I figure I might as well just combine the fractions on the left. And as I say here, because I otherwise don't see anything convenient. So as I combine them, of course, my common denominator is this one here. And then, of course, I come out with sine squared, and I come out with 1 plus cosine squared. On the left-hand side, I might as well multiply out the 1 plus cosine squared as a perfect square trinomial, and that's what you see here. And then what I also do is I could multiply the sine into the parentheses, so distributed, but I recognize that on the right-hand side, the cosecant needs a sign in the denominator, so I would amend this one here to say keep sine alpha in the denominator on the left because of cosecant alpha on the right. That's kind of a foresight. Let's see, I need to change this to alpha. And there we go. Okay. Then I see on the left-hand side, after I did the algebra in the numerator here with the 1 plus 2 cosine plus cosine squared, that I have a Pythagorean. Sine squared plus cosine squared comes out to 1. And that's all that happened here. Now it's starting to look nicer. I recognize that now in the numerator I have 2 plus 2 cosine alpha, so I factor out a 2, and there it is. And then I notice that 1 plus cosine appears both in the numerator and the denominator, so I cancel it, and that leaves me with 2 sine on the left, and of course the original 2 cosecant on the right, which I recognize as being reciprocal, and I'm done. Okay, let's go to the next example, where I have to show this. 1 plus sine over cosine equals cosine over 1 minus sine. I readily recognize it as that when I cross multiply here, I'm going to come up with a difference of squares. So I'm going to do that. Here's a cross multiplication, and then of course get the cosine to the right hand side. That way I get rid of all denominators. On the left hand side now, we have a nice difference of squared. 1 minus sine squared equals cosine squared, and that maybe not immediately, but pretty soon I recognize as that really looks like a Pythagorean. In fact it is, and we're done with the proof. Okay, from that I'm going to go ahead with the graphing calculator, where I say check the graphing, with a graphing calculator, and we can do that in 2 different ways, where we say that the diagram, let's see, this is actually what I wrote later when I was done. Yep, that was all done later. You can check identities with a graphing calculator by graphing both sides of an identity, or by plugging in a check number. If you plug in a check number, you have to be careful. Don't use special angles. The reason for not using special angles, but instead use 10 degrees or 20 degrees or something like that, or 1 radian or something. The reason for doing so is that, for example, look at this one here. This one actually is not an identity. But if you happen to plug in 60 degrees, you come up with an identity, because now you have 1 plus cosine 60, which is 1 plus 0.5, so 1.5. Sine of 60 is square root of 3 over 2 times the square root of 3 is 3 over 2, again 1.5. So coincidentally, you come up with the correct result for 60 degrees, but not for any others. So be a little bit careful with these here. Here's the easiest case for a non-identity is that sine equals cosine. Well, it's obviously not correct, but it will only do so for 45 degrees and 225 degrees. And let's see, 225 degrees and 305 degrees. That's not quite correct. Okay, this is not quite correct. I have to think this over and rewrite it. Oh, I know how to write that right away here. Typing 360 degrees as well as 225 degrees plus, okay, times 360. And of course, we know that this one cannot be an identity because it doesn't work for any other angle. But an identity has to work for everything. So, in essence, when you check numbers, try some unusual ones like 10 degrees, 20 degrees, 43 degrees, 58 degrees, something like that. Okay, let's actually go back to the 2 identities that we worked with earlier and go to the graphing calculator. The last one here, we're going to graph and see what we come up with. I have to shuffle through my notes here. Okay, let's go over there. All right, we're going to graph that, and so we're going to have 1 plus sine over cosine. Oops, don't need that second parentheses. And we graph that. And there it is. So it's the left-hand side. And now we're going to graph the right-hand side, which is cosine over 1 minus sine. And I made a mistake here on purpose. What you read right now here is actually cosine over 1 simply minus sine. But that's not what it said in the identity. It said cosine divide by 1 minus sine. So you have to make sure that you put the denominator in this case, and in the first case, the numerator in parentheses to tell the calculator, hey, this is really my denominator. Okay, when I graph this one here, it's just going to graph over the other one, and in essence, we're not going to see anything. So what I'm going to do instead is I change the graphing to make it bold, and then we'll see that as it graphs right over the other one in bold, that the two sides are identical. And that's what I was supposed to show here with the graphing calculator. Notice this is not a proof. The proof we just did for all these examples algebraically, but graphing is just a test. Check it out on the graphing calculator, and indeed it looks correct. For the other one, we're going to do a plug in a number. So I do the right-hand side first because it's easier. 2 cosecant alpha. I don't have the cosecant, so I do 2 divided by sine of 10 degrees, for example. Enter minus 3.676. And I have to amend here 10 degrees. I forgot to change from radians to degrees. I was graphing in radians because it kind of squeezes my graph a little bit better than in degrees. So, but I forgot that. In any case, it actually doesn't matter. So I'm actually plugging in 10 radians. You will see that an identity, of course, has to work for both degrees and radians. So it really doesn't matter. I'm going to type in the left-hand side now. So that's going to be sine of 10 divided by parentheses 1 plus cosine of 10 degrees parentheses plus the numerator in parentheses 1 plus cosine of 10 degrees. No, do I keep saying 10 degrees? I mean, of course, radians. 10 radians divided by sine of 10 radians. There we go. Now I figured it out. Okay, now I'm going to cross my fingers as I'm hitting the enter button. Not because I'm not confident that it is an identity. We already proved that. We showed it algebraically, but I crossed my fingers that I made no typo on the graphing calculator. And indeed, I didn't. And you can see that the two sides are equal. And that means that, at least for 10 degrees, it's an identity, and then all likelihood it's going to be the same for all other degrees, radians, and we of course have already shown that algebraically. Let's go back to Word because I want to mention a couple more things. So here I already plugged it in from my mute recording from earlier. And then I'm going to go down here. Yeah, here's why. Second time around I did the same thing there with the 10 degrees and the radians. Let's see. Anyway, I already talked about all of this here. And then the very last thing in this lecture is be familiar with the other identities, as we will encounter all these identities, sum and difference formulas, double angle, half angle, sum to product formulas, lots of them. Recognize the patterns, but don't memorize them. You don't have to memorize them. You have to just know where to find them and then recognize them and see what the patterns are. There would be just too much to memorize, so when the test comes up, I'm just going to give you all those identities. What you have to memorize are the basic identities: ratio, reciprocal, Pythagorean identities. And with that, I conclude the lecture on proving identities.